Welcome everyone again to Mass Timber March Madness, the second week. Happy to have Brad Nile of Andersen Construction here to explain a few of the many projects Andersen Construction is working on in Mass Timber. Before we begin, I want to thank, as always, the U.S. Forest Service for their support and the Tallwood Design Institute. Welcome, Brad.
Thank you.
I think let's test your screen sharing and I'll let you take it away.
Okay, are we looking good?
We're looking good.
Okay. So good morning. Thank you, Greg, for the introduction. Thank you for the opportunity to be here. So what I'm going to focus on today are some of the unique elements or accomplishments of the mass timber projects we've built. And this is from the context of North America, specifically Oregon. So with that, I'll start the presentation. All right, so here we are, Andersen Construction. We have offices in Boise, Eugene, Portland, and Seattle. And here's images of some of the mass timber and heavy timber projects we've built over the last 6 years. Here's a little biographic slide of me, 26 years with Andersen Construction. I am an architect, but also a compulsive builder. And here's 6 decades of projects in my spare time. When I wasn't building large-scale projects for Andersen, I've had many, many adventures in woodworking, including in 1978, my very first glulam beam that I built for my parents' house, along with my mom and brother there. So is everything working okay? Keep going. I'll take that as a yes.
Yes, everything looks great.
Okay. So I'm going to start with Oregon State University, the College of Forestry, known as PV, and MGA, Michael Green's office from Vancouver, BC, and Equilibrium Canada, were the structural engineers. I'm going to focus on 2 unique elements, rocking shear walls and then a 32-foot clear span that we did in CLT. So this first bit, post-tension rocking shear walls, here's images of the completed space. You can see the shear walls in this case are fully exposed, and you can see the tensioning rods were left exposed as a teaching element. And then in this case, there's some deformation brackets that help dissipate energy as these 2 independent elements are tied together. And you know, the story behind this, we're going to do a deep dive into how we built that. So there's, of course, hundreds of hours of collaboration and sketches. And I always get the teams together and we're constantly sketching ideas. And this particular image, it's having to do with, okay, how do we get the tensioning apparatus installed, and how much clearance do we require, and how do we measure tension accurately, how do we monitor tension, so that we're sketching out the load cell, the coupling, the bottle jack, the reaction frame. All of those elements were pre-planned very, very early. Here's more sketches. Okay, we got to get 50 kips load on these tension rods as they're coming up. And then the whiteboard was too small, so this is a sideways sketch of the 48-inch anchor bolts to the anchor plates that eventually return all this load back into the foundation system. Of course, everything's fully modeled. This is modeling by StructureCraft. And you can begin to see the ghosted image in here. I just took a snapshot of an early printed copy, but these are the walls that we're speaking of. All of these planes are post-tensioned shear walls. Of course, the question is, how do you get the post-tension rods into a CLT? And because we were using 2x6 lam stock, we simply omitted 4 lambs to get those rods in on alternate layers, alternate longitudinal layers, right? It was quite simple. Yeah, there was a little bit of glue in there, but that gap at 1 3/8 with the 1-inch rods, it was perfectly easy to assemble those, prepare the CLT, and get the rods installed prior to standing them up. Here's the foundation anchorage. So if you look here on the left, there's actually an embed for a horizontal shear block to prevent the base of the CLT shear wall from sliding. And what we did, we stretched out that embed to form the bolt template for then the boundary element anchors for the CLT panel. These, of course, are the 4 rods anchored down 4 feet into the concrete. Here they are in exploded view. Here's one of the rocking shear wall panels at the shop. All this prep work was done at Structurecraft shop. You can see these are the deformation brackets that are at the boundaries, the edges, and that's where that shear block engages the horizontal, that prevents horizontal sliding. And of course, back here you have the slots waiting for the post-tension rods. Here they are going up, right? On the left, that is, obviously these walls have to go first and then the structure ties in around them. Here, of course, here's a isolated singular longitudinal shear wall. These are the boundary anchorage with the deformation plates that dissipate energy, along with the post-tension rods that return this shear wall in a major seismic event. They return the shear wall to the upright position. Of course, for those boundary anchorage, here's that shear block was field welded. We oversized these holes so that there was a certain latitude, a certain construction tolerance, and then there were weld washers applied over the top of those anchor bolts, and then they were nutted down snug. Just more images of that going together. Again, that same little more context for that installation. And here we are at the top. So you can see there's enough room to get a load cell, a nut, a coupling nut, and then the donut jack, as they call it, in order to tension those. This case on the left, this is a mechanical shaft that is bounded by CLT rocking shear walls. So we had to anchor the base of this to a wide flange beam in the basement, so the ductwork was free to pass beneath and go up. So you can see it there. Worked quite well, right, with those web stiffeners. Here's a little more in situ arrangement, and then here's the finished product, right? This is prior to tensioning on the left, and then on the right that is after tensioning. And a large number of these locations we left the load cells in permanently, and the university is monitoring the tension so that they can, not only was it extremely useful to calibrate our tensioning apparatus and technique, it allowed us to then understand and understand the sequence with which we tensioned and then retensioned. And then we now have that long-term data to understand any potential shrinkage or elongation of the steel. And of course, we're waiting for the big earthquake, right? And then that'll be really exciting data. Okay, next item is this 32-foot clear span, right? Okay, look at this atrium. There are no beams, right? It's just a 32-foot 7-ply CLT concrete composite clear span. And I'm going to tell you the story of how we did that. Of course, it started with there is a back span and cantilever. And this image on the left is how we engage those 32-foot panels to the back span. Right, quite a simple approach. And you'll see here that there is a char layer left to protect that steel. So up here on this image on the left, I find my mouse, that is that joint that was made by that Z profile. And this photograph is taken in September, the second week of September. And of course, a film crew from England arrived that day, working for a nonprofit, talking about the impacts of the global impacts of mass timber construction. And of course, it was raining on the day they visited. And as you can see, we'd advanced our way across this atrium, and then we had to pause and install these sloped elements for the feature stair. So here we are looking at the underside of that third floor. There's that same splice condition. Here's the back span of the cantilever. And of course, there's shoring required to ensure that they don't deflect prior to the casting of the concrete. Here's the preparations for the concrete to go down. Again, more whiteboard sketches, 3.5 inches of concrete with a water-reducing admixture. There is rebar and there's hydronic piping. And then there, of course, there are shot pins anchoring stud framing down. And then, of course, diagonal screws, insulation, and double acoustic mat. So this is a complicated sandwich that we're making here. On the left, this is actually on level 2. And once the rebar and screws were in place, we laid out where all the partition lines existed to ensure that there was no hydronic piping placed there. This image on the right, that is level 3, and there is a single partition line. And obviously there's a no-fly zone right here where there couldn't be any anchorage of partitions. But this demonstrates kind of that overlapping of acoustic concerns and hydronic heating, as well as a composite long span. And there it is. On the left, you can see the mid-span shoring. So we actually introduced a slight crown to the 7-ply CLT. And obviously we didn't want any deflection prior to the curing of the concrete, so it had a dual purpose. And then on the right, you can see that slab. The couple days after it was cast, we polished the concrete, and we left that shoring in place 28 days just to be sure. And here's the outcome. This on the left, that's upstairs. That's directly over that long span. And of course, from below, you've seen that image. And of course, there it is upstairs again. Quite stunning. All right, moving on, the project in Portland, an office building. There's 2 things I want to talk about here. There's a mass plywood stair and there's a CLT elevator shaft. Mass plywood stair designed by Hacker, engineered by KPFF. And of course, the mass plywood was fully fabricated by Freres here in Oregon. This connects 2 floors within Hacker's office. And mass plywood. So this was, of course, fully modeled and fully CNC fabricated into these stringer tread assemblies. And there they are on the left, flying them in bundles of 3, and then staging them on the floor, ready for installation. And that is, these are raw. This is just how they came off the CNC. Then there's structural steel, obviously supporting the landing, but otherwise it is an integral, essentially becomes an integral slab that includes tread, riser, landing, spanning from level 1 to the landing, and then landing to level 2. And here's the installation, and I should say level 5 to level 6, to be clear. Here they are, some glue and some screws, and here's the finished product, working obviously very carefully to ensure that each layer was perfectly aligned with its neighbor and perfectly level and flush. And then it was just a day's worth of sanding to mold this into a single piece of mass plywood, essentially. Okay, next one is a CLT elevator shafts. Same building, concrete lateral system. And at the ends of the lateral system, instead of continuing more concrete, we advocated for the use of CLT elevator shafts. 5-ply. The only complication is that they had to be detached at each floor. But this is a scene. It was a Kone machine roomless system. And there it is. There's the elevator machine mounted at the roof level to the side of the CLT elevator shaft. Here's some more scenes of that going together. On the left, you can see that the first floor was a tall story, 16 feet. So there had to be supplemental steel that was dapped into that elevator panel. Then on the right, you can see here, these are the rail attachment brackets, because we wanted the rails to be attached to the floor deck so that in a seismic event, these panels would be free to move without encumbering the engaging in any lateral restraint. And of course, these are brackets left behind from our forming system. And as soon as the elevator team was mobilized and had their work skip installed, we then removed those brackets and returned them to our concrete crew. But this is essentially that elevator going up, or the shaft going up. Unfortunately, our fabricator misunderstood the finished face. So they prepared a beautiful interior face and left the outside unsanded. And that had to be corrected on site. So here they are. Here's a pair of elevator shafts adjacent to the concrete core system. And, it's left in its, this is a number 2 and 3 lumber with no wane, basically, and unfilled. So it has a slightly industrial appearance, but it makes an excellent elevator shaft. It was the lowest cost scenario in this application with a certain amount of unforeseen complication and ensuring its detachment from the lateral system, but it was a successful outcome. Of course, there it is on the finished floor, those elements on the right. Okay, moving along here, side yard. This is Skylab and Catena. And incidentally, I'll be taking questions at the end. And so I'm happy to peel backwards to get back to where the location of the slideshow that makes the most sense. But this is a little mass timber building that was the structure itself, the timber structure was prepared by Cut My Timber. It's Skylab is the architect, Catena is the structural engineer. It's right at the geographic center of Portland at the east side of the Burnside Bridge. And what I'm going to talk about is the CLT formed concrete core system. And so there it is on the left, that's the concrete core. Obviously, you know, we're 5 stories, we need 2 exit ways. And we also need a lateral system. And in the end, we chose to do it in concrete and utilizing number 3 industrial unsanded, number 3 grade lumber, unsanded CLT as the form panel. So here's an image of the job site, you know, very compact, dense little piece of property. And on the right, you can see CLT form panels going up. Obviously, they were approximately 10 feet wide as they were assembled, as they left the factory, but they were pre-cut with daps along the edges so that we could spline them together. They were pre-drilled for the strong bats that we then installed, and pre-drilled for the ties that worked with a pre-engineered standard interior box system. And here's just images of those panels as they came off the truck and were ready to be utilized. One other thing that we did, we chose to pour 2 levels at a time because of the strength of these panels. We could easily withstand the form pressure of a 24-foot lift, right? Or yeah, 24-foot lift. And that's not normally something that we like to do to large style gang forms. We prefer to limit a pour to 12 to 16 feet, but given the strength of this system and the relative low density of the rebar, we chose to do double lifts, and it worked beautifully. And we just had 2 cores, 1 set of forms that just bounced back and forth. So here on the left, you can see 1 lift is in place, and you can see the blockouts, the doorways to get in. And yeah, kind of a dramatic shot on the right, showing again, these panels are now into their 2nd lift and they're almost done. And part of the thinking here is that all of the forming components are 100% reusable. So here on the left, that's the interior, that's a pre-engineered system, right? It has the retractable corners so that you can retract the corners, then slide the walls back, lift it up, and we jumped it from core to core. This is the interior form finish that you get on the interior. And again, we're not allowing the architect to design this, we're allowing the form system to dictate the form lines and tie pattern. Just more scenes of the system going up. Obviously, there's pre-installation of all of the embeds and electrical components. And there they are just about to top out. So for level 5, we cut the panels in half, and those panels are now, they've been built into a barn out in Clackamas County. But there you go, there are the CLT formed cores. On the interior, we did a mass plywood stair in there as well. You can see the landings anchored in. And of course, we had embeds. Because it is the lateral system, there is intensive engagement with the CLT deck system. So with those embeds positioned with enough latitude for a certain amount of adjustment, we had the floor ledgers being anchored, and then we also had beam brackets being installed. And of course, if you look at the CLT, you can see how the base of the CLT is dapped out to land on that ledger and account for the specific geometry. And there it is. There's another block out there for a beam to come in. It's pretty remarkable when you have a fully modeled structure. And the other thing that we did is we fully modeled the concrete, and we imported our concrete model and shared it with the Cut My Timber model. And we also did, of course, to make sure that all the concrete and embeds were designed to align with all of the interconnecting timber. Of course, we then did an as-built survey to understand any adjustments, because it's you know, it's not, we are with concrete, we are not as accurate as the timber, to be honest. And here we are, finished condition. On the left, you can see that core is, you know, you get a lovely finish. The more we use those forms, the more character there was to that form finish. And there was no sack and patch. It was just, you place it and you take the forms off and you're done. It's quite remarkable. And well, the patch, we did have to plug the holes, right? It is a 2-hour fire separation. So we did have to patch the form ties, but there's so much character to begin with that the relative position of those form ties, and there's no longer a fixation with panel position and alignment. And here's on the interior, it's simply the raw concrete. And this is the stair assembly that we installed, built also from Ferris mass plywood. Okay, I'm going to conclude with the story here behind the OSU Emerson Lab. This is back at Oregon State in Corvallis. MGA, the architect, and Equilibrium Canada, the structural engineer. It's a fabulous building. And the story that I want to tell here is about, this is more part of the mass plywood story, because the lateral system for the big box, the big testing lab, and the exterior wall assembly is essentially mass plywood. That's all there is. It is mass plywood, weather barrier, thermally broken supports, insulation, and cladding. So at the time, the APA certification for these structural panels was literally a few weeks old when we received these panels in 2018. Of course, let's not forget that this is a testing laboratory, and there is a dense infrastructure of rebar and anchor bolts in the floor of that big lab area. So Ian McDonald, if you're watching, just go ahead and try to pull those things out of the floor. Good luck. So just a little snapshot of that massive amount of structural strength that lies beneath the floor. Here's an aerial shot. You've got that strong floor off here. Where's my mouse go? We've got the strong floor over here, and then we've got this is basically shop area, back of house, shop area, offices, seminar room. Here we are going up in August. Here is the forms for the strong wall. And of course, the strong wall simply has sleeves. So each of those shiny bits represents a set of 4 sleeves, so that you can then put through bolts and again, just try to pull that thing over. So here's the structure going up. So this is 4-inch mass plywood panels that were delivered to the job site at 12 feet wide, 20 feet long. It's just fabulous. So on the left, you can see as it's advancing, as it's progressing from east to west. And here, this image gives you a sense for the just what a thin structure that is. It's just remarkable. So that's a 4-inch panel that's standing up 50 feet, and it's tied in every 20 feet to a glulam column. And then of course it projects up to provide a small parapet. And then there is a DAP at the horizontal joints. So there is a plywood spline that goes in at the DAP right there. More images of this going up. This is the grade of the veneer is a structural veneer. They refer to as dime C. So it's a C face with no open knot larger than a American dime. Right, and you can see this is all second growth, young, relatively small diameter trees utilized in this veneer, and it creates the most amazing strong material you could fathom. Of course, these are the rest of the structure, glulam beams. Got to give credit to glulam beams from Zippo in Eugene. The CLT panels, excuse me, the mass plywood panels. So that's an entire panel, 12 feet wide, 40 feet long. The joists were LVL from Murphy, and then there were PSL as well as LSL, LVL studs from Boise Cascade making up the rest of the building. So the entire structure is built of engineered wood products. And because we're doing this in September, we are advancing the roof assembly as the structure advances. And this is when you call in all your friendships and favors to make sure that your roofer is willing to work with a relatively small crew. And you advance 20 feet, you get that nailing inspected, you put up the safety rails, and then you commence roofing while the structural team is advancing the structure, so that when the structure was done, within a couple days, the roof was done. And here's some interior finish shots. This is the seminar room. These are PSL as well. And then on the left, you can see glulam columns and wind girts over the polycarbonate panels. And of course, that's just the polished structural slab. And one last interior shot showing, again, that rhythm of the 20-foot bay spacing with the 4-inch mass plywood. And then obviously there's a large beam to make the giant opening. And look at that happy forklift zipping right out of the lab. And of course, I wanted to end here with a photograph of yours truly with my friend Red Emerson. That is the man for whom the building is named, the founder of Sierra Pacific Industries. And he was very kind enough to obviously contribute to this building and be in attendance for the grand opening. And we shared stories. I grew up in Northern California, and my father was a friend of Red's. And it was kind of a fun highlight, I guess you could say, of my career to be there at that grand opening and connect with Mr. Emerson. So, Greg, that is my last slide, and I am now prepared to take on questions if you want to fire them off to me.
Sure. No, thank you for doing a deep dive into specifics of your projects. I think that's very interesting in showing the unique things you're pushing forward in Oregon. First question comes in we got a couple from Scott Noble. It's at district office, were you able to leave the CLT exposed inside the shaft, or were you required to encapsulate the shaft side in drywall? That was the
district office, sorry.
Yeah.
No, Hacker went to bat on that issue and was able to demonstrate, no drywall on the interior. It remained 5-ply CLT, and they were able to demonstrate sufficiently to the city of Portland that wood assembly was both non-structural and essentially acted as a 2-hour fire assembly.
Okay, and then a couple more from Scott. And at district office, given that typically the rough opening for the entrances are absurdly large, can you talk about how you infilled the shaft wall to the entrances and maintain continuity in fire protection? Wow.
Oh, it's a fabulous question. Outstanding question. Well, yeah, well, I mean, part of the reason this worked is that this, yeah, it wasn't built like a fine Swiss watch. It was built in the just basic elements. So what we did, Scott, is we had an oversized opening. So this is a panel, this is a panel, this is a finger panel. We had an oversized opening because at the time we were ordering the CLT, we hadn't finalized the elevator selection. Then the hoistway doors were positioned and installed, and there is a small sheetrock wall assembly that is a metal stud and sheetrock wall assembly that engages the jambs of that opening, jambs of the elevator hoistway opening. And in the typical fashion, those hoistway doors are designed to engage drywall systems. So we did that. Then Hector designed a stainless panel to conceal the drywall at the head. And then we simply put another chunk of Douglas fir in the plane of the adjacent panel and glued it in. So to answer your question, we had a rough opening that became the finished opening thanks to a margin of metal stud framing and drywall. And the other great thing about that, it provided a conventional way for them to rough into metal studs all the controls associated, all the elevator controls.
Thank you for that. And here's a question. Before we started the seminar, we were discussing the record-setting prices for timber, and even the lack of availability is essentially sometimes hard to get. Scott asked that question: what is the approximate price difference between CLT and MPP, mass plywood panels? It's
I'm not going to comment. Mass plywood, when we were building, how can I say this? When we were building the Emerson Lab, mass plywood was the cheapest option. Mass plywood was the lowest cost alternative, right? When compared to metal stud framing, drywall, and just imagine that metal stud framing, or wood studs and plywood. I mean, or CLT. We ran through all of those scenarios, and this was the lowest cost exterior wall assembly. And of course, the MGA design with the bold openings with polycarbonate panels, it all just snapped together so incredibly well.
beautiful. Here's a question from Sina Jahedi. On the design side of things, what are your thoughts on the comparison of mass timber buildings versus concrete buildings? Designing which one is more cumbersome, time-consuming, and expensive?
So it depends on scale and complexity, right? And so if I zip all the way back here to the opening scene of district office, this is 100, there's one level of underground parking, and this is on the east side of the Willamette River, right? So there's a river there. This is Stark Street. Stark used to be essentially a creek, right? And so there are deep foundations, and this is fill, right? This is essentially built on fill. So there are deep foundations. So at this end of the building, our deep foundations are, there's drilled concrete shafts down to dense gravel. They're 14 feet from the bottom of the parking deck. At this end, they're 120 feet, okay? So there is a deep variation in the depth of competent soils or densified material that we can found the building on. And timber was the cheapest option. Concrete, we ran concrete scenarios. And when you add the mass of an entire concrete structure to soil conditions as, I don't want to say poor, but just challenging soil conditions, the foundation became significantly more massive and costly, and timber was the most economical option. It is easy to, I mean, we are skilled builders, right? I mean, there is a system worldwide to build efficiently in concrete, right? All these buildings, all three of these buildings were projects that I built here along that skyline in the Pearl District, all out of concrete. And the code understands it, the engineers understand it, the workforce understands it, and the rental, the form systems are highly developed. So concrete comes with all of those advantages, but it's incredibly massive, and it has a completely inverted carbon story when compared to a timber structure. So I don't know if that helps, but you know, and part of the reasoning that this structure, you know, hats off to Hacker and KPFF, there is uniformity and repetition and simplicity and directness to that design that works incredibly well. It is, where am I? Yeah, it's a very, very efficient structure on a, we look at the cubic volume of timber per gross square foot of building. This is the best we've done.
You're certainly well qualified to answer the question with that extensive experience on both building types right next to each other.
Well,
Question.
I just noticed that, yeah, look at that. Yeah, that's the tallest concrete moment frame in the state right there. So anyway, go ahead.
Yeah, this one, sorry if I'm not pronouncing the names correctly. This is Alex Leger. I don't know. Could the elevator, I don't know, manufacture, is that MFR work without having supplemental steel for the guide rail attachments?
Yeah, no, that's a great question. So yeah, you can buy excuse me, you can buy stronger rails capable of spanning more than our basic floor to floor is 16 feet, and asking an elevator rail to span 14 feet is okay, it's reasonable. Asking it to span 16 feet, there's very, very few people are willing to do that. And it comes with a premium and a lead time. It is simply faster. It's more direct and less costly to simply install that supplemental steel. And what it is, they basically got up to the 14-foot mark and welded a bracket to that chunk of tube steel. It was that simple. These were confirmed with Kone. And these two rails here are this is supporting elevator rail and counterweight. This is supporting counterweight. This is supporting elevator rail. And so, yeah, even in concrete structures where there's where you have shaft wall, anything beyond 14 feet, in my experience, the rails don't want to span that far.
Thank you. Next question from Zach Moreland. Hi, Brad. Zach Moreland here. Did you consider leaving the CLT formwork in place after forming the cores at side yard? Also, what sort of moisture barrier did you use between the CLT and concrete? Beautiful projects.
Okay. So at side yard, the CLT formwork was just that. It was formwork. It was ideally every concrete core that we built would be this size, and we would just leave them at our yard and we would reuse them hundreds of times if we could. The CLT that was utilized for that formwork was removed, and it's now in a built structure. And so I can feel pretty good about that, because in the past it would have been plywood that probably would have ended up in the dumpster. So there's a story of reuse. We did do the same thing at district office. We used a similar approach. And it would be possible to actually use those panels in a floor or roof assembly in the structure, but they're just deeply stained with concrete and form oil, so they don't necessarily have a second life. Now there is no, and if you're asking about a separate question, leaving or how we waterproof this layer, in this case it gets it gets acoustic mat and gypcrete and then a built-up floor assembly. And what we did is we used a topical waterproofing and then seam tape to ensure no bleed through. And then we put the acoustic mat. It had to be 100% dry. Acoustic mat and gypcrete. District office, I go back there. Same thing. This is a structural topping slab full of rebar, and it has screws that help engage the slab to the CLT. And again, it's a topical waterproofing. The CLT must be dry, topical waterproofing, and seam tape to ensure limited or no bleed through. And you can see there's a slab cast above here, and you can see very little bleed through there. No acoustic mat in this case.
We have a next question from Sujit Bandari. Hi, Brad. Great to see your presentation. The tolerance between concrete and mass timber is one of the challenges in mass timber construction. What checks and tricks does Andersen have up its sleeve to account for the differences and tolerances between the two materials?
Yeah, I have to thank Hacker. On my mouse, this image kind of demonstrates that. Yeah, you can see what we had here was a reveal, just an old-fashioned reveal. And that reveal pushed that sealant joint further back out of sight, and it allowed these two planes to have variation, right? You can kind of see flush here, and you can see a bit of a shadow here. So it was just the old-fashioned technique of a appropriately sized reveal that was, we obviously had to account for the fire rating of that assembly, but it was just the old-fashioned reveal between those two different elements. And part of it is just enforcing a higher level of accuracy to our concrete crews, model the concrete, as-built the concrete, monitor it progressively. And honestly, we have room for improvement. And sometimes maneuvering a giant form box in space and ensuring its true vertical alignment is not as easy as you might think, but it's something that, I refer to all of this concrete as go like hell concrete, right? We simply had to, this is a speculative office building. There was not, there wasn't a willingness to pay for fine architectural concrete. All right, we needed to go like hell, and that's what you see. And so this is also CLT formwork, and it gives you the freedom to move very quickly because you're not aligning form panel joints, right? That's the whole reason that I advocate for it. And my friends at Hacker weren't fixating over the position of these elements because they blended into an overall ununiform pattern of boards. I don't know if I've answered your question, but yeah, it was a way to accomplish very quickly a exposed permanent concrete structure without paying the premium for architectural concrete. I don't know if that makes sense. I'm not sure that many of our competitors would gladly jump on board with this approach. There's a lot of pre-engineered form systems readily available, but we wanted to do something where we could go quickly, but have an appealing finish that, yeah, everyone is very happy with the exposed finish on the exterior of these walls.
Next question from Jonathan Hepner. Given your experience of constructing the rocking wall, could you relate any particular observations that might encourage their utilization in mid-rise or high-rise structures?
You bet. No, these are fantastic. Splicing them, I guess, Jonathan, probably the biggest challenge is developing the splice, right? And so what we had, long threaded rod dowels that were epoxied in, and on the backside we had injection ports. So there was a special inspection and QC I'm not sure where my mouse went, exercise in making those splice joints. And if there's any way that we could have had that done in the shop and had them shipped full length, that would have been a huge advantage. I think it's jurisdictional adoption is probably the biggest issue. Yeah, I mean, just imagine the amount of concrete and steel that was saved by, a relatively simple device. I'm just kind of thinking out loud a bit. The concept of these deformation brackets is that in that major seismic event, they will deform as they dissipate energy and have to be replaced. I can't see if there's any engineers on the call nodding along with me, but you're preventing the catastrophic collapse of the structure, and you're able to reuse the entire structure after a seismic event. because the only elements that suffer damage would be these deformation plates. Right, there they are. And then that boundary anchorage, I can't say there's anything I would do different to do this again. And we just got to get the jurisdictions on board with this approach. And yeah, there was enough planning went into this that there was very little drama ultimately. And yeah, I guess this model shot kind of helps tell the story of those rods and the splice. We obviously didn't go as tall as was modeled originally. Hope that answers your question, Jonathan.
Here you've got a question from Stefan Schneider. It says, amazing projects. Where do you see the biggest challenge for mass timber buildings compared to steel or concrete buildings of similar size as the building shown? Is it cost? Is it being a new material or process? Is it code and regulations? What is your take from an industry expert point of view who has completed many concrete and wood buildings?
I feel like we have, let me just sort of run through a checklist. We have architects and engineers who embrace wood structures and want to build in timber. Right? I haven't met an architect or engineer yet who has said no thanks. Everyone that I work with is keen to see further utilization of timber. Clients, however, are at a certain point, it becomes just a basic financial question. And we've been asked on almost every institutional project that we've worked on, except the College of Forestry. College of Forestry, you know, there's no way in hell they would have built out of anything but wood. But there's other clients that have to know. At some point, somebody's writing a check. There is somebody in an office who there's a financer or an equity partner, and they don't give a shit what the experience of the building is. They just want to know, would it be cheaper to build this in steel? And for low rise, small scale, sort of suburban commercial buildings, it's really tough, right? By the time you don't save enough in foundations going from timber to steel on a low rise building to demonstrate foundation savings. And there are the delivery model for steel structures is so developed and mature, right? No, there's no inventing details. They're all in the AISC book, right? It's just, here, we'll use these details and it's this big and poof. And when we are put head to head, especially small, you know, suburban type office buildings, we can't cross that line yet. So it's the challenge becomes sort of educating the client beyond the numbers, right? And this is something Woodworks has worked awfully hard on. It has worked really hard to demonstrate whenever possible that at a large enough scale, the cost differential diminishes and we achieve parity, if not savings. And the building is significantly more appealing to the occupants. And there's all those other, there's the experiential benefits that, you know, somebody at the bank's not going to necessarily understand until you can link it to things like the lease up time or the rate of leasing. And I think if you were to look at the T3 projects that Hines has done in Minneapolis and Atlanta, those are textbooks examples of the scale and repetition and simplicity, simple utilization of mass timber in a way that works financially for an organization that's essentially there to make money. No offense to anybody who's out there. Any financiers on the call. I don't know if I answered your question, Stefan, but you know, I'm kind of on a mission to just communicate beyond the numbers, talk about the experience and talk about the sustainability aspects. right? The carbon sequestration, the renewable resource, the benefit to rural economies. I mean, all of these things are real, and you can't talk about any of those things when you're putting up a steel building.
Right. Here's a question from Lech Muzinski. He said, can you envision a cost-effective weather shedding of the construction site at the scale of the buildings presented?
No. Yeah, I'm not sure what to say. Like, yeah, would I prefer to build these dry? Would I prefer to have a structure to protect this? I just can't. I don't know. I think some of us over the years have seen, I think it was Obayashi America or Obayashi in Tokyo would have a giant tented structure over their buildings as they went up. And we have simply not been able to rationalize that extreme expense, and instead have attempted to, number one, build during the dry months whenever possible, and then just have really thorough and intelligent protection of the detailing, targeted and precise protection, and just expediting the facade installation. And I think you just don't want to bookend a fast timber structure with slow elements, right? And I don't know if any of my images here demonstrate, like when we put this little building up, the best we could do here was to prefabricate wall assemblies that were fully waterproof. So when that wall panel went up, it was fully waterproof. And then the issue was expediting the window installation. And of course, the roof panels were at the factory, the CLT plant, there was a temporary roof applied so that it went down and the seams were sealed, and we then immediately put some pumps up there to ensure that there was no ponding, and we were able to then protect the wood. And then if there is kind of the bigger picture of dry out detailing. So detailing the structure in a way that acknowledges it will get wet. Okay, once it's wet, how does it dry out? And how does it dry out without the formation of mold or decay, key, and without excessive checking? And those things cost more and they take time. And so we're walking this fine line between spending enough money, being responsible builders, and protecting the structure and not wasting money. So how's that for a long answer, Mike?
That's great. And you are getting a bunch of compliments in the chat. Fantastic, informative presentation, amazing presentation, great presentation, just so you know. And here's a question from John Boyce. Can you talk about finishes on the wood elements, shop applied versus site applied?
Yeah, well, yeah, not much to talk about. Nobody wants to do it. Nobody wants to do it in the shop at this scale, right? I'm not sure. Ideally, this would be pre-finished, and it would be pre-finished, and we wouldn't be worried about any field application. In this case, what was installed in the factory was a Sanson KP12 UV. So we've got basic short-term protection against moisture, and we've got UV protection against sun tanning. But otherwise, it's essentially a raw wood interior, and that's the finish that this client wanted. The stair obviously field sanded and field finished, right? There was no way to make an assembly like this pre-finished. And then I guess, so yeah, this is all field finished, no pre-finishing here. Then if we go back to PV, again, the scale of these elements, our industry isn't set up to pre-finish elements at this scale. They would do 2 or 3, they would do a few trusses, but at this volume, we just haven't found anyone willing to take on that effort to pre-finish. And in this case, it was erected, it was fully dried, inspected, and then sanded. And there is a light blonding to this wood So there is a light stain applied to this wood, and then 2 layers of clear finish. And in this case, it was all done in the field after the structure had been erected. And you know, Lek, I know your question about, well, can't you protect this from moisture while it's going up? This project had the intense disadvantage, what's my word? I guess we had the intense adversity of having a material failure early in the assembly of this structure, where there was a flawed fabrication technique that resulted in an unbonded layer on certain panels. And so that structure stood longer than it should have out while we analyzed the root cause, determined the extent of product issue, removed all the defective elements, and then replaced them all. And so, yeah, we ended up working on from many fronts at how to protect the vulnerable elements. And then once they were completed, to inspect and verify, dry them out slowly, and then apply the finishes. Well, I went off the deep end on that answer. I hope that's okay, everyone.
Well, I know Lek was in Sweden, and in Sweden it's pretty common to essentially build a large tent structure during construction. But yeah, that's just not happening in the US.
Well, I would love that.
Yeah. Here's one more from Lek. Can you comment on the savings in the pace of construction and assembly compared to concrete or steel, excluding PV project, of course?
Oh, okay. So this district office was the first time we delivered on that promise of, yeah, faster than steel, faster than concrete. And again, it's the scale, right, and the repetition, and you know, all of this structure went up incredibly quickly, right? We were as long in the ground getting those deep foundations in as we were erecting the structure. And so yeah, it was fantastic. The other aspect about this is that the tenant improvements are relatively simplified. If I just zip forward here, because this design accounts for sort of longitudinal utility distribution in a beam-free colonnade. You can then distribute transversely alongside the beams without having to ever go under beams with ductwork. And then there's also utility chases that Michael Green started using a number of years ago that allow sprinkler pipes and small conduits to travel efficiently longitudinally. Excuse me. So when you kind of take all those factors together, the fact that it went up very quickly, ideally we'd have a fully prefabricated facade system clipping on. We weren't quite there yet. And if we had the facade of Brock Commons on this building, that would have been astonishing to have seen how quickly this could have been gone from, grade slab to dry envelope. It would have been incredibly quick. But the TI build out, the simplification of the TI build out, there's very few ceilings. Yeah, there's ceilings in conference rooms and washrooms. But otherwise, what you see is the structure, and you're not spending the time to conceal or fireproof what are otherwise, relatively ugly timber or concrete elements, depending on your point of view.
We're coming up on 10 o'clock, so it's been an hour. Why don't we take one final question? This one is from Luciano Tagliaferri. He says, very nice presentation. Which size of wooden slabs and columns did you apply? And do you think the tendency of the size of wooden elements is going to increase in general?
So yeah, that's a great question. So, and this is a perfect slide. So you look at the width of that board. That is a classic North American Douglas fir board, right? That was a 2x12, and those don't grow in Europe, right? You can't go to the lumberyard and buy a 2x12. Once it's glued up and planed, we're down to 10 3/4, right? It comes from the planing mill at 11.5 inches. It gets glued up, it gets planed on both sides, and you're down to essentially 10 3/4 width. I guess it comes out 11 and a quarter is a 2x12 width. So what that means is that that is the widest element that we can glue up from a single board in our North American fabrication techniques. Right there, you can see there's a finger joint there, and finger joint, stack them up. That could go 5 feet thick, right? You could just keep adding lamella to go as deep as you want. So I am always recommend this as the maximum width if we're buying North American glulam material, because we're not as facile and skilled at block laminating, sort of making up that width from 2 boards, right? We don't have that edge gluing side compression that would be present in a more sophisticated fabrication system. So yeah, within this width of 10 3/4, that's fabulous. And mind you that it does include a char layer. This is a 1 hour structure. So the other option is to make a smaller column, use less wood, and then apply gypsum to it. But that, yeah, most clients are relatively, yeah, they're just simply not interested in that approach. So I think in North America, we need to get better at making wider elements out of glulam so that the block laminating appears with the same fine joint quality that the successive lamella have. We need to be able to achieve that on the width gluing of wider timber elements. And of course, this beam, I think, is 30 inches deep, right? And that could have been much deeper, but that was optimized for the span and fire rating of that element.
Well, thanks, Brad. It's a great presentation. I learned a lot. If it's okay with you, I'd like to include your kind of LinkedIn connection as if people want to follow up with you after the event. Is that okay with you?
Yeah, I need to pay more attention to LinkedIn. I'm not ignoring all those people out there.
Well, it's okay, and it's up to you. It's up to you whether you want to share your email or other contact information, but I leave that up to the presenters.
Perfect.
Okay. Well, thank you. Today is one of the days we have another talk at 10:30. This one from Fabian Scheuer of Design to Production. So I want to give everyone a break a bit, 20 minutes before we start with that. But thank you again, and I do expect to have these presentations up online in the next 24 hours, the ones that have happened thus far. Thanks again, Brad.
You're welcome. Thank you.
Thank you, everyone.